start to do like this?
Yeah. Yes. Okay.
Okay, but some of the time I'll be like some of the time you're gonna see my back rather than my head.
Yeah, that's fine. So they can see the people here. So
Oh,
we
okay,
try
okay.
to bring the
So
participant to come.
okay, like this then.
Yes.
Okay.
Okay. So thank you everyone. So the next session will be the keynote speaker talk. So today we have Dr. Evelyn Sender. So she from George Mason University, and she working in dynamical system and mathematical design and visualization with a focus to 3D printing. And now she serves as the editor-in-chief of the SIAM journal on applied dynamical system. And previously, she served as session editor of SIAM Review Research Spotlight Session. And she also the editor-in-chief of the S-Web magazine. She have previously until now 5 PhD students, and she also mentor a lot of undergrad research projects. So we are very happy to have you here, Dr. Evelyn. So her talk today will be about stable floating configuration for 3D printed objects. So I'm gonna leave the stage for you.
Thank you so much. Yeah, thank you. It's a real pleasure to be here. Thank you for the invitation. I'm gonna so this is my talk in a jar. So I'm gonna pass this around so that you can do the same kind of discovery that led us to think about this. So what I want to have you do as you're thinking about this is to think about the fact that when you put this in the water, it floats in a certain way, and if you turn it, you can get it to float in different ways. And so, you know, just try this with the G and the M. The U is actually sinking to the bottom, so you won't have any luck in getting it to float because it is too heavy. So let me pass this around. You can try it out a little bit as I'm talking, and like I say, have some discovery of this yourself. I think that the nice thing about 3D printing is that everybody can, you know, I have a GM and U here, but in fact, let me pull it out so that you can be trying this as well. I have also an F, an A, and a U, so feel free. That's right. And so anyway, so with this, let me talk a little bit about this is research in two different groups within the math department. The first is MEGL, which is a design for research experiences for, it's vertically integrated, so undergraduates together with graduate students together with faculty. And then let me talk about my research group. So all of this research is with my colleague Dan Anderson, and we've basically had a different group of people every semester. So the first semester here is the group, they started actually before I arrived. So the full year of 21-22. In the fall, we had a new group of researchers shown in the middle, and that group was just for the fall. And the third group is this semester, and I don't have a picture of them yet, but it's nice because we've been able to work with whole bunches of undergraduates as well as a few graduate students and getting them up to speed on these ideas. Feel free to pass around the A and the U as well if people want to float them. So before getting started on the technical ideas, let me say that it's like fun to float things, right? But one of the inspirations for the idea originally is to ask the question, why do icebergs float in the way that they do? And what happens if some part falls off, which is called calving, and they readjust? How can you understand the way in which they're going to readjust to float in a different configuration? And so in order to understand these, there are a few ideas from physics. First of all, the mass is just going to be an integral of the density, and this is shown in a two-dimensional case, but obviously in 3 dimensions, the same idea, but a triple integral instead. And here I'm using the omega to mean the domain, which means the floating object. The center of gravity, which is basically the balance point of the object, is evaluated by taking whatever the mass of the object times the integral of x, where x is a vector because we're talking about a location either in 2 or 3 dimensions, times the local density of the object. Once you introduce water to the question, or fluid in general, the question is where on the object, how far up is the object going to float? And so in order to understand this, what we need to understand is the center of buoyancy. And the center of buoyancy can be understood as the amount of water or fluid that is displaced by the object. So in other words, instead of measuring the center of gravity of the object, we're essentially studying the center of gravity of the fluid that isn't in that place anymore because it has been displaced by the object. So the principal thing that's involved in understanding the floating configurations is the Archimedes principle, which says the upward buoyant force exerted on an object wholly or partially submerged is equal to the weight displaced by the fluid. So in other words, the object is going to float in such a way that the mass that it displaces is the same as the mass that is submerged. So that means that heavier objects are going to be sinking because they displace more than their mass, whereas very light objects are going to float very high in the water because they've already had a large volume displaced while lying high above the water. And so this is translated into the volume submerged over the volume of the object is equal to the density of the object if it's a uniform density, or the effective density if it's a non-uniform density, which means just the average density, divided by the density of the fluid. And just as an example, you know, when you hear that 90% of an iceberg is below the surface, that's because the density of an iceberg object over the density of water in the seawater is equal to around 90%. And the question is how to, so this is going to be an important value, R, capital R, I'm going to call it, right? So this is the density ratio that's involved. If you were to float things in oil or syrup or seawater rather than water from a water bottle, all of these would change your value of R, but the theory would be the same. And so I don't have to redo any diagrams, just knowing R is all I need. And so for a 3D printed object, keep in mind that I'm talking about, I don't know if any of you are 3D printers, but I'm talking about the plastic PLA. There are 2 major plastics that people print in. There's ABS and PLA. And the plastic that we used is PLA. And so the information here is about PLA. And the way that you can change the density of an object that's 3D printed is through the density of the print. So the print is solid on the outside, but it's somewhat hollow on the inside. It has like either a honeycomb or grid pattern inside. It's not fully filled. And so the result is that depending on what the density is of your infill, you're going to change the density of the object. And so anyway, if you did 100% filled, it would sink. If you did something less than 100% filled, you can get it down to about 0.3, and you can get it down even lower. But as you decrease the density further, it becomes more and more non-uniform. So I'll talk about that in a minute, but it's something to keep in mind. So the potential energy. So let me just say that one of the things, and you can notice in all the things that I've passed around in the water. I don't know, where did the water? Okay, yeah. So you see in these objects here, I think I have another one here, right? So all of these objects are long objects with a fixed cross section. And they're printed in such a way, they're printed like this so that the infill is exactly the same. So even if you slice this open, it would be identical cross sections in every place. This is sufficiently long that we can reduce it to a two-dimensional problem because it's not going to be affected. It's going to lie along the surface on its long side. And so we don't have to think about how it's going to float in terms of the long direction, and we only have to worry about the cross section. And so the result is that we've reduced to a two-dimensional problem, standard mathematical trick, reduce the dimension, and we're able to just consider the question of having the cross section and asking how does it float. In order to answer the question of how it floats, what we would like to know is, let's say that this is 0 degrees from the original configuration. What is the orientation in degrees that it's floating? Now, another trick, it's a lot easier to move the water, which is a nice, well-defined line, than it is to move the object. So although as you change the orientation, really the object would be the thing that changes. What we're going to do is change the water line. So you notice that this water line is now sideways. So think of it as taking the photo at an angle rather than having the water stay fixed and the object change. And that just makes the analysis a little easier. So anyway, with this in mind, Gilbert in 1991 developed a potential energy for a floating object. This potential energy is just minus the mass times the gravity times the normal to the water line, which remember, the normal to the water line, if you were going to keep the water fixed as horizontal, would be vertical, but the normal to the water line is now changing because we're changing the water line. And then times G, where G is the center of gravity. So the work required to displace the fluid is given in this form. And basically using the Archimedes principle, and I'm going to go through this rather quickly, we can see that the potential energy is given in this form, the mass times G times this N, dotted with the center of gravity minus the center of buoyancy. So in other words, you're taking a vector that points between the center of gravity and the center of buoyancy, and you're taking the dot product of that vector with the normal direction to the water line. And to say that this is a potential energy, the minimizers of this function with respect to theta, the angle, are going to be the stable floating configuration. So just to point out, and this is something that you observed as I passed around this water, is that, and if you ever were in a kayak, hopefully you didn't observe this by experiment, there's more than one stable floating configuration. Okay, so one of these is more desirable than the other with the kayak, but anyway, they're both stable. And icebergs similarly have multiple stable floating configurations, although the only way that it would change is if, once it's stable, it's not going to change unless there's some dramatic event. So long objects with a fixed cross section have been studied before. The square, the rectangle, and the equilateral triangle. There's also a conjecture, the Oulom's floating body problem. The question is, in general, which cross-sectional shape would result in no preference as to which way the object floats? So in other words, every floating configuration is a stable floating configuration, if you wish. There's neutrally stable in the sense that there's no preferred direction. And obviously, then this is the Lumberjack World Championships log rolling. This is the case of a circular cross section. That's an obvious one where there's no stable floating configuration that is preferred. And this shape on the left is more surprising. At a fixed value of R, this shape actually also has no preferred stable configuration. the thing about this is that we wanted to have, this seems like a really interesting mathematical problem, but we wanted to have something that would be practical to do experiments. And it's not very practical to do experiments on a question of no preferred stable floating configuration, because the slightest inaccuracy in your print is going to result in it not being actually true anymore. And so we opted to not study this problem experimentally simply because it would be impractical to do so. So we have developed a code that basically just automates the process. You give it a shape, and the shape is defined as a polygon, in this case, a square. You can see in pink the square, and then the code goes through each possible angle of the water line and evaluates the potential energy. It's just a dot product, right? And then it plots it. And so anyway, you can see here for the square, if R is 0.1, you get 4 stable floating configurations. The minimum you could have is 4 because it's completely symmetric in fourfold. You can see that 0 is one of them, and so in fact, I may as well just show you in the water. That this is actually on the other end of things, but it's a flat floating configuration. On the other hand, if you increase to 0.2332 and a range around 0.2332, what you get is 8 stable floating configurations. And then if you increase to 0.5, what you get is 4 stable floating configurations, but they're corner down instead of side down. And then if you increase further, you see the same thing. It's a symmetric procedure. So this is the very low in the water. This is more like 0.9. And you can see that it's flat side down again. So I just want to say something about our computations. So we actually designed this code that you just give a ordered set of vertices for a cross-sectional shape, and it's a polygon, and it has to be done in oriented, so it has to be done in such a way that it's counterclockwise rotation, right? And then use and compute the center of gravity, the center of buoyancy, the mass, all of these things. And I just because I love Calc 3, just want to mention that this is actually a summation that you can use Green's theorem in a nice way to find. It's a simple summation to do all of these calculations. So anyway, but the point is that we're able to do this, identify the water line, the center of buoyancy, the potential energy. And so here are some other polygonal shapes that, so the thing about the square is you can actually do an analytical calculation in order to get all the square information. These shapes could presumably be done in that way too. It's just going to be much harder, but we can automate the procedure by doing a numerical calculation. And once you and you can see that, like in some of these cases, the number of stable configurations could be predicted by the symmetry of the object, but in other cases, you wouldn't necessarily see that, right? You wouldn't know from looking at the arrow how many stable configurations there would be necessarily. Once you realize that you can do this for a polygonal region, you can also realize that everything is a polygon if presented correctly. And so this is the GM and U in here, and the FA and U, in case you were wondering. These, unfortunately, I didn't have time to carefully make sure that the R for these objects was the same as the objects I actually printed. And so this would be something where it isn't necessarily the case that these are the stable configurations you'll see for these particular objects. I just chose an interesting choice of R and plotted this diagram. Okay, so with this in mind, you could ask the question, you know, it'd be nice to be able to just visualize for all R at the same time, what are the stable floating configurations in terms of angle? And so this is a picture. This was already known to read and others. But what this is a picture using our software, and this is basically what I've described before. If it's high, if the square is high in the water, it's floating flat side down, then it's going to have 8 stable floating configurations in this intermediate area right here, where R is around 0.25. And you can sort of, if you were wondering why 8, you know, where do these come from? You can sort of maybe see it now that it's going to be sort of sideways and then other sort of sideways on each corner or side, whatever you want. And then corner side down, and you can see clearly here, there's a long range where it's stably corner side down, and then the same thing in the other direction as R grows larger again. So it's symmetric both with respect to the square symmetries, but also with respect to R through 1/2 R. So because we have software to do this, right? We can just go ahead and make the same kind of plots. These are more computationally intensive because for every one of these, we need to use basically a numerical minimizing calculation for each of the values of R in order to find the corresponding thetas that are local minima. And so here are some pictures for the arrow, the star. The G, M, and U are a little more interesting because you can see that they're basically patterns that are stable here, but then just disappear at some value. So if you're wondering how that can happen, if you're familiar with bifurcation diagrams, the point is that studying minimizers is really not studying the full bifurcation diagram. Studying the minimizers is part of the picture. What you really should do if you want to see a nice connected bifurcation diagram is to study the extrema. And so these points here are points where presumably there is a turnaround and a saddle node bifurcation. So there's a minimizer and then a maximizer going the other direction that meets up with this diagram. So just if you're sort of somebody who's interested in this, I did not do the F, the A, and the U, but if you're interested, I'll make sure there's a copy of the software. You can try these out and see what the stable configurations are as a function of theta for this F, A, and U. Or the owl, since it turns out that would have also been a good choice. So I just want to make a few comments about design. So there were 3, so far I've been sort of talking in big picture, but there have been 3 different semesters of work, and there are 3 different concentrations of this work beyond just the question of developing this software to compute the stable floating configuration. So the first semester, we concentrated on the question of non-uniform density for simple objects like squares. And so OpenSCAD is a CAD system which is command line based, so more closely related to something like Python than many CAD systems, which are like you're moving things around with a mouse. But in this case, it's much nicer to be able to design with specific points because we're feeding in the polygon with vertices into MATLAB. It's nice to have the same polygon be used for the design of the 3D printed object. And there's very simple ways to do this. And I'm showing here that we wanted to study non-uniform density. So one of the things we did was to put a hole in and to put a nail into the hole. And just to give you an idea, experimental work is messy and doesn't always do what you want. And so you end up with a whole bunch of squares, which are labeled and, identified in various ways in order to test various things. But one of the things we did was to put a nail hole and then to basically cut off a nail and put the nail in so that we could control the density. So you had to do a lot of, from the mathematical point of view, trivial stuff like accurate weights and making sure we knew what the densities were, measuring things like, for instance, even though this infill controls the density, you can't really say that it's necessarily uniform And because on the outside, there's a shell, a protective shell to make sure that the thing is waterproof. Waterproof, well, like that it floats in water and doesn't get waterlogged. And so we had to do a fairly large amount of testing. One of the things that we also had to test is that the density information on solid PLA varies enormously in terms of what the reported numbers are. And we found that it varies brand by brand as well. And so in order to predict what's going to come out, it's sort of problematic. We had to do a lot of calculations. And anyway, after this, we did some initial testing of the square with uniform density. And you can see that our dots are our experimental results, and they agree well with the calculations. We then were sort of inspired by the fact that, especially at low infill, you get non-uniform density, to try to control this better, putting this nail in and asking the question, how is this going to affect our calculations? And so using the same kind of ideas before, we made these R versus theta plots for the non-uniform density cases of nails being at various levels along, and calculated what the theoretical predictions are. And you can see the dot represents what we've actually measured. So in the first bottom left case, you would say that we've done a pretty good job. For the second case, this is surprising because there are two stable configurations that are nowhere near an actual theoretical prediction. And so we had to go back to the picture of the original. And what we realized is that it is an issue that we're very close to a bifurcation point where one of these stable configurations appears close to where there's been nothing before. And so what we're seeing is maybe through a slight change in the density from what we actually measured, or a slight change in the non-uniformness from what we measured, this results in getting to this stable configuration that wasn't measured at the place we saw, but was measured for a nearby density. And here, same kind of idea for the Mason M. And you can see that our predictions are the red. Our predictions are given in blue, but the red dashed lines are pretty close to where we expected to see the stable floating configurations. So the next step, this is the second semester, last semester, was we wanted to move beyond the question of just floating in water. So the question of what happens if you have an object like this U that sinks in water, but maybe floats in something denser, or maybe you have an object like this one, which floats in water. This is the same one in the picture. What if you pour oil on top? So now it's gonna sink. If you were to just try to float it in water, in oil alone, it would sink in oil, but it floats in water. So what that means is that when you pour oil on top of the water, it's going to be lying in the interface between the oil and the water. And the question is, what happens to the stable floating configurations in this case? And you can see that something has clearly happened, because when we float it in water alone, it's side down. When we pour oil on top of the water, it immediately reconfigures in such a way that it's corner down. So the question is, can we say something about what's actually happening to those configurations? And so the answer is yes, using a bunch of analysis. I'm sort of trying to avoid getting too technical here. The original one fluid case, the value R1 is equal to the density of the object, if it's a uniform density, or effective density if it's not, over the density of the fluid. But in the two fluid case, you can actually reduce it to the one fluid case in the following way. The effective, the density ratio for the two fluid case is just going to be the density of the object minus the density of the lower fluid over the density of the upper fluid minus the density of the lower fluid. Okay, so in other words, it's still a density ratio. It's just that you have to include both fluids in the density ratio in order to make this calculation. So once we've done that, we can actually use the same diagram, this R versus theta diagram. It's just that R is now a different ratio instead of being the original ratio. And so this here, these dots are the predicted case of the one fluid version of this object, this black object, and the green dots are the predicted location of the two fluid case of this object. So you can see that we're able to successfully predict that it will go from a flat side down to a corner side down just by pouring oil on top of the water. Obviously, this depends on the fluid you're using. And so we did some experiments. This is another experiment. We tried to identify cases of the square where it would be a more interesting case, like for instance, in oil, we predict that this object is going to have 8 stable configurations. And you can see this is off center, which means it has to have 8 stable configurations. In water, this should have 4 stable configurations all flat side down. And in oil plus water, it's going to be corner side down. Here, another experiment: sinks in oil, sinks in water, floats in syrup. It's messy stuff, by the way. And also very, like, I mean, when they talk, this isn't molasses, this is corn syrup, but when they talk about slow as molasses, I now understand. We had, you put it in water, you see immediately what the stable configuration is. You put it in syrup and you wait about 5 minutes for it to settle. It's like settling down slowly into some stable configuration. But anyway, the water and syrup case, you can see, is quite different from the syrup case where you have 8 configurations, and now you have okay, so this here is going to be the 8 configuration case, right, at a 0.75 density. Here, this is going to be the 4 configurations case, but with a 0.35 density, which is quite different.
But you talk about water and syrup, water and oil.
Yes.
So water and oil, that's fine. Oil from on top because they don't mix each other. But water and syrup, they are going to quickly.
So not as quickly as you would think. So we asked some people who are amateur bartenders, because our bartenders in general make these layered drinks. And so they know how to do it in such a way to avoid having immediate mixing. And the answer is you use your muddle spoon and you pour very slowly onto the muddle spoon, and that avoids any mixture. But what happened was that we did, I will go to this case, okay, where we had the G lying on the top of the oil, the M lying between the oil and the water, and the U lying between the water and the syrup. And we loved it so much that we left it in my colleague Dan's office for a long period. And over time, he would come in every day, and this is the original way that this U was floating. And as he came in every day, it was very slowly moving, and you could see, actually, you could sort of see this mixture area where there had been, over time, the diffusion had actually caused the mixture to start happening. And by the end, it was actually floating upside down, and it was really cool, but unfortunately, it molded. So we had to get rid of it. But anyway, so it's exactly what you said, and we were sort of inspired. We haven't done the experiment yet, but one of the follow-up experiments we want to do is a speed version of this to actually mix water and syrup in prescribed ways to see how this transition occurs. Yeah. The syrup is corn syrup. So I like it's professional corn syrup. So I don't know that, I mean, but it definitely is mixable with water. And you have to do, it was like maybe a few weeks. Yeah. So anyway, I want to talk a little bit about this semester's work. And so I have a story. This semester's work is about surface tension. We're concentrating on surface tension. And let me just say that before I printed the large FANU, I printed very small FANU. And because they're pretty much all made of surface and no interior, they all sink. I will show you that they all just sink to the bottom, right? But the thing that's interesting in sort of like making the best of the situation is if you place them down very carefully, you can get them to float on the top, okay? And that's surface tension. That's all surface tension. And so, you know, it is, these objects are small enough that surface tension is an effect. Another application of surface tension is water bugs, which are able to stay on the top of the surface despite being so dense that they should sink because of surface tension. And actually, fire ants, when they get into floods, they have a collective behavior where they form a big roll in such a way that there's surface tension by having all these ants close together that causes them to float, even though each individual ant would sink. And so there's lots of cases where surface tension are interesting. So far, we're sort of at the initial stages of the analysis, but one of the things that we have done is there's the way that a water bug moves on the surface, and understanding this will move us from statics to dynamics, is by the Marangoni effect. And what this means is a surface tension is a force on the object, and different fluids have different surface tensions, right? Different tensions. So if you have two fluids that are meeting, then if they have a different surface tension, this is going to cause an interaction that actually can cause a force that can propel the object. And so this is something that water bugs use in the water. They'll be sitting in the water, and the question is, how are they going to move? There are many different ways that they move, but some of them excrete out of one end. They have an excretion which has a different surface tension than the surface tension of water. And the result is that it actually propels them across the water. And so we have been doing some background reading about this. And one of the things that the sort of classic thing is a soap boat, which is using the Marangoni effect as well. But it also works equally well with isopropyl alcohol. And so we read a very unusual collaborative effect paper by John Bush, who is a fluid dynamics mathematician who is interested in water bugs, and Jose Andres, who is a top chef who has restaurants all over the world. His base is in DC, and so anyway, they wrote a paper together on cocktail boats. So these are little tiny boats that will propel themselves around a mixed drink. So we didn't want to do that, but we were interested in looking at this effect, and I'll see if I this is, let's see, I'm gonna have to do a new share so that people online can see it. So this is one of the students made this little boat that was described, and this is putting a little bit of isopropyl alcohol into the boat. And you can see it propels itself nicely around the little, I think it's just a glass. I mean, the object is maybe this big. So, and one thing I would say is that that it was surprising how this did not take a whole lot of, I mean, the theory is going to take us a long time. And so doing something systematic and doing some analysis of this is going to be quite involved. But if you were interested in sort of a 3D printed object that would be a follow-up to something like what I've talked about with these stable floating configurations, designing this didn't take her very long. She had only gone through a few of my tutorials on how to use OpenSCAD, and she was able to design this quickly, and it worked on the first try. So I think this is like a nice add-on for students who are interested in floating objects. And I don't know how much time do I have. Okay, so I want to demonstrate the code, but I feel obligated. I have been tasked with making a shameless promotion first. So let me make sure that I get my plug in here. So we would love to see math majors at any level at George Mason, but this particular task that I have is to advertise that we have a PhD program at George Mason University, and we have a large variety of faculty. The students get jobs who have graduated have gotten jobs in a variety of different types of locations, including we're in the DC area, so government. We have a pretty good relationship with some of the government jobs, like we've had people at the Naval Research Lab, at NIST, at NIH, and so we have a funding of $25,000 over 9 months, as well as opportunities for summer funding. If you're interested, there's still openings, so feel free to apply for this semester, or not this semester, sorry, this coming fall. But anyway, just keep it in mind, and so please do send your applications our direction. And now you know, all of this research is both with undergraduates and graduates. So if it's something if you find appealing, or even if you don't, there are people doing all kinds of things. So there are many different opportunities for you. So now I've done my task. I really would love to see you at George Mason if you are able to apply, if you're the right stage. Now let me move back and talk about demonstrating this code. I think for this, I'm going to have to, let's see, I need to share my whole screen, I suspect. And now what I want to do is show you a couple of different things. Let me pull this down. Okay, so the initial, most of the work is in MATLAB combined with OpenSCAD. And so let me just go ahead and first demonstrate the OpenSCAD idea. Okay, so this is going to be there's a let's say that you find a picture of a duck on the internet, okay, and you think, oh, well, maybe that would be a fun thing to print, okay. So this is what I did in order to make the FDA and the U, is I just took a screenshot of the Florida Atlantic symbol and then downloaded it. And then what I have is this thing, figures to points. Okay. And what figures to points does is, and this is the sample usage, is you have to give it some information, what you want to make figures to points, and what file you want it to be in. And so I just run this thing, and it gives me the data on the screen, but it also saves it, and it also makes a picture so that you know, yes, this is the duck that I thought it would be. It's particularly useful if there's more than one color. It might not be able to distinguish what you really wanted to see. And so once you've done that, then in the original folder, what you'll see is that there's now a file called duck. duck.scad. There's also a file duck.mat, which is the MATLAB instructions, but this is the duck.scad, which gives in a set of points to be used in OpenSCAD. And this make float here, you have to change to include duck.scad, you would have to change it to whatever your folder is or your file is. But this has created in real time this long thin duck. I think it's pretty straightforward to understand that this height is 70. This is all in millimeters because that's what you need for 3D printing. And you can see that the duck is a pretty good size, but if you don't like the size of the duck, you can scale it using the command scale. So there's a lot of fairly straightforward things to do. Once you've gotten something you like, you render and create an STL file. That's all there is. That little ding was to say that it had created the STL file. The only thing that's a little problematic is that the location of the STL file is always a mystery to me. You have to look, I don't know where it went, but that's regardless of whether I knew where it went, it would be different on your computer. So that's like one problematic thing about OpenSCAD is where did the STL file go? But anyway, with that exception, I would say that it's a pretty good design for this type of thing. It's pretty straightforward to do. So with this in mind, now let me demonstrate something else. Just a sec. So I have a code demonstration of the code that I have just been using. All right. So this is just showing you what you would have to have the whole folder. And then the first thing I'm going to do is just add the path to some subfolders. And the reason I've done that is that in these subfolders, I have provided a bunch of shapes like the arrow, the end-on, stuff like this. And in the complex ones, I have the Mason M, stuff like this. All right. And so then once you have done that, I'm going to just go ahead and add the shape arrow. And then one thing you can do is to just plot the shape. So I have written the code in such a way that it can be used as a black, I don't know what happened to the plot, just a second. Here we go. You can use this as a black box, but you don't have to. This code is pretty easy to edit. It's just that if you didn't want to, you don't have to, it already works, right? And so the reason for the red, the green, and the blue points is so that you can double check that you actually do have a counterclockwise rotation, because the rest of what I'm going to say will not work if you don't. In fact, what it'll do is all the local maxima will be the ones that are actually the stable configurations. So if you have it counterclockwise, it's important. If you have it clockwise, it'll give you exactly the wrong answer. So once you've done this, you can do this. So let's just set the density ratio has been automatically set to 0.8750, but I can also change the density ratio to, let's say, 0.83, just for fun, right? And then I can do the potential energy calculation with this shape and its density ratio, and it comes up with a plot. Yes. I'm just setting the density ratio here. The density ratio was set in when I said arrow, that also set the density ratio, but it's fixed for fixed materials, right? No, the density ratio, well, the density ratio is an abstract, right? This is just R. So R can be whatever you want it to be, anywhere between 0 and 1. unpredictable results if you go below 0 or above 1, and meaningless anyway. So 0 and 1, but anywhere between there, right? So I can change this density ratio to like 0.98, and then my potential energy calculation gives me another picture, right? And so then, okay, so this is a bit more labor intensive. This one finds the actual floating configurations. So it doesn't look a whole lot different. And this is the one exception to, there's a little problem there. The floating configurations are going to look correct, but the water line is in the wrong spot. This is a bug so far in the program, is that the water line is not in the right spot, but the direction of, the way you, like, it's going to be in the right orientation. It's just going to be floating in a different place than it really should be. But you can see that this is a more labor intensive calculation, because in order to take that picture and figure out the exact location of the angles for the stable floating configurations, it has to do a fair amount of work. So what it does here is it shows you each of the stable floating configurations. So this means that you can compare your solution to this actual picture. Okay. And then the last thing, which hopefully will work without too much extra time, is that you can make the theta plot. And this is, whoops, this is the thing that those pictures of the R versus theta. Okay. So with all this, you can make your own object. You can test what the object stable floating configurations are in general and in any particular density. If you have a scale and weigh your object, you can also find the volume of the object in various different ways, but like finding the volume. Okay, so here is the stable floating configurations for this object R versus theta. If you find the mass of your object, as long as you know the area of your object and also the length of your object, right? So the length is not going to be very hard because you've set that. It was set as 70, right? This is 70 millimeters, but you would have to set it yourself. And then you would have to also know the cross-sectional area, and that's a little bit more involved. It can usually be found using the 3D print software, but which is what I've had students do this in an undergraduate class, and I just have them open their object in Mesh Lab, and one of the things it'll tell you is the volume of the object, which is one way to do it, but you can also calculate this using green theorem. But anyway, once you have that information, you will be able to, and you can look up the density of your fluid. If for water, the density is 1 if you use the right units. And then you can basically figure out where on this diagram you lie. And then you'll be able to test your object and see if it floats in the way you expect. And let me just make some comments about this. If you see an object that has a lot of, so if an object has a lot of edge compared to the center, it might float unexpectedly differently. And that's because the edge is going to be heavier than the center. And so it's not just a matter that you have a different density on the edge, it's that is going to actually, unless it's completely symmetric, that's going to throw off your calculation of where the center of gravity is. And so this means that you might have a different center of gravity, which means that your object is no longer uniform, and so it's not going to float in the same way. But if you make your object slightly larger in every direction, or use one that has mostly interior, then you get a pretty good way of doing this. So anyway, I'll go ahead and let's see if I can pull up the I'll go ahead and end with sharing the screen again so that I can put up some references in case you want to read more. The first reference is we've written a paper that is going to be in the proceedings of the Symposium in Applied Math, the AMS publication, and we're currently writing up the second set of the two fluid interface case, and maybe in the future we'll be able to also say something about surface tension in a publication. So thank you so much.
Thank you so much, Dr. Evelyn. So do we have any questions?
Sorry, I may have missed this because I was going to step out, make sure everyone's stuff was safe. The fire alarm door went off.
Oh, good.
Everyone's stuff was still there. So maybe I missed this, but it sounds like you said there was a relationship between the object sinking and having an inside versus outside. Like you said the small F, A, and U, they're all, there's no interior, so.
Well, so the point is, let me go back to the
We said about interior, as you said.
yeah, so these diagrams, like these diagrams here are showing, if you know the density of your object, then you can find a calculation of the potential energy at each angle, right? At each orientation of this object. And the local minima of this this energy diagram are going to be the stable floating configurations of the object. But the calculation that we're doing here relies on having a uniform density. And so this object, for example, has a pretty close to uniform density because it has a large amount of infill, which is a fixed density, and a very small amount of exterior, which is a different density because it's being filled 100%, whereas the interior is filled at this one maybe 30%. And so on the other hand, this object here, okay, has very little infill that's being filled. And so it's probably uniform density, but unfortunately the actual uniform density of this object, and this is why we have to worry, is such that actually, unless you count for surface tension, it's going to sink to the bottom of the tank.
Right.
And so we're in a position where we can't use a uniform density of 100%. We have to use an infill percentage in order to make it float. But what that means is that if you have quite a lot of exterior shell, then that's going to have a non-negligible effect on your density. And in particular, make it non-uniform. Yeah.
So it said that in those diagrams, the local minima correspond to the stable configurations. So in that third diagram, there's looks like three stable configurations, but one of the minima is higher than the other. What would be like the interpretation of that?
So probably not as important that it's higher in absolute as it would be that it's the distance, like the distance to the local max is the key. Because if this thing, so let me just show you in this case, right here, these are technically speaking stable configurations, but you would expect them to be very difficult to keep because just a slight perturbation and you're going to get an energy that causes you to move away. Yeah. So I guess the person, I don't know, they're not online, but I was going to say this is also something that you have to worry about in the Cahn-Hilliard equation that we heard about earlier. You get this kind of a question of energy wells, and if you have not in the sphenodal region that Melissa was talking about, but in the nucleation region, you actually have to account for that quite a bit in terms of like the depth of the energy well is a critical piece in trying to understand the stability.
You mentioned some of the parameters, density or whatever, would have bifurcation, depending on, did you do any sort of analysis of that, like a bifurcation diagram or?
Well, so these are not quite bifurcation diagrams in the sense if I wanted the full set of critical, the full set of extrema, not just the local stable minima, I would have to have other things on the curve that show the unstable pieces. And so we didn't do that. I mean, so there are like various ways that we could have done this. One way is to use numerical continuation, start at one end here at angle 0 and say, okay, well, we expect to see probably the same, locally the same configurations as we did before, although there might be bifurcation, and then sweep along and follow. So that would be a numerical continuation method, but we chose not to do that. And instead, at each value of the angle, we just did a new calculation. And so we don't have a full bifurcation diagram with all of the unstable the most unstable configurations on it. We just did the stable one.
I think I have a curious question that may be stupid. You talk about surface tensions. Now, I think ducks float on water. But chickens, ducks, yeah. But chickens, I think, I don't know, I've never done a chicken there, but I think they will sink. They have about the same shape, about the same density, about the same thing here.
Well, so I mean, okay, I would rather not comment on ducks and chickens, but I can tell you about like objects. Okay, so for example, if you take an object that has been 3D printed and you put on a special coating, a certain kind of paint that is that's like the kind of paint you have on your car, it totally changes the way it floats because the surface tension changes. The surface tension is not, so the surface tension is what causes this meniscus that you see, right? But the surface tension is not just a matter of the material, but also of the sort of the, like whether you've sanded it, how smooth the material is, and so, or a coating, and so you can change a lot. So I mean, ducks. Okay, I'm going to say something about ducks, which could be completely wrong, but it seems like ducks maybe have more of that kind of a coating that would cause them. Yeah, so like they kind of seem to repel water, right? So maybe this is a way of changing the surface tension. But on the other hand, the thing about ducks is that that they're too big to have surface tension be the real effect, right? Because like a human, whether a human floats or doesn't float actually is not about surface tension, right? Because we're just too big. If you have an object that's small like this, like a paperclip or a Cheerio, or one of these very small objects, you can get it to float by surface tension alone. But a water bug could not work in the same way if it were the same weight as a human, because the surface tension becomes a negligible effect at that point. So I don't know if ducks versus chickens is a matter of surface tension. It seems unlikely to me because I wouldn't expect that to be an effect at that particular weight.
But maybe next semester.
That's right. That next semester will be floating ducks and chickens.
I don't know.
Yes, thank you, Dr. Evelyn, for the talk. Let's take
All right, guys, so that's our talk. So I think before we break for lunch, our Fab Lab director, Linda, just give us a brief tour around the Fab Lab, just show off all the people visiting again at 75 years.
Yeah, and if you have any questions, the keynote speaker, we can talk during the lunch, okay? Thank you.
So.
Here,
Oh, that's awesome. That. Thank you.
Right now, that, this is a chapter. Essentially, this is where we not the engineering kind of student. So now, like when you go to school, so now, like, you learn all kind of equations and then all numbers. But at the end of the day, we experience from most of that. And you can know how, like, how even though it works to real life, and you know how, like, the drawing from the drawing application, how it's all over the shape on the drawing, like, actually animate. So we do that way to look at the mechanical experience. So in here, we have lots of these things. So we have 16 conventional NVM figures. So it's just kind of like, basically it's not plastic, and then you can talk about that, talk again later. On top of that, we had two special figures right here, SLA figures.